In this module, you will be doing tests on the mean and confidence intervals for the mean. What we will be doing here is using a lot of formulas, and we'll have a few conditions to remember on when to use these techniques. Now we are going to be using the central limit theorem again. To review, the central limit theorem will allow us to use our normal techniques given that we have a large enough sample size. Now the new standard deviation for the mean of y, the distribution of the mean of y, will have a standard deviation that is the true standard deviation divided by the square root of n. And this works under circumstances when we have a large enough sample size. Review the module with the central limit theorem to remember how the central limit theorem works and what large enough is. So with this in mind right here, a 95% confidence interval would look like this. But under most circumstances, we won't know the true standard deviation. We're going to have to come up with a different technique here than we had for proportions. Because when we had proportions, we could use z of 1.96, which is basically 2, to make a 95% confidence interval. And this comes from our 68, 95, 99.7 rule. But we can't use this because we don't know the true standard deviation. And you'll see what we use in a second here. But we don't know this, so we can't solve this formula. We're stuck. So let's use S instead. But we can't use this because it's not going to work either, because no longer do we have a normal distribution. So in this instance, we're going to just try to plug in S, because we don't have sigma, which is the true standard deviation. We have the sample standard deviation, but now 1.96, there's a problem with that. We can't use that. So what can we do? Well, going back to the late 1800s and 1900s, people really didn't know what to do here. And they kind of just made assumptions under most instances. And what they did was not always the best. And they saw that because their techniques had problems. Well, along came William Gossett. And William Gossett, very true story, worked at Guinness Beer. And interestingly enough, he made what's called the student T distribution. You might say, well, why is it not called the Gossett distribution? He was worried he'd become so famous that he was like, I don't want all this fame and fortune that's going to come with the student T distribution. And so he didn't name it after himself. You'll ask what it is, but you'll see in a moment. The student T is going to look just like the normal, but it comes with something extra. It comes with degrees of freedom. So the degrees of freedom is going to be based on the sample size. So the student T, there are millions of them. Because think, you can make a million different sample sizes. In truth, there's actually infinite student T distributions. You say, whoa, how do I know this thing? There's infinitely many of them. How do I know what it'll look like? Well, as you can see right here, we have the normal with the hashed line. And then underneath that, we have the student T distribution. The student T distribution is actually a push-down normal. I always say Mr. T comes in and says, I'll pay the fool, and smashes down the normal. If you'll notice right here, it says this T distribution right here has 2 degrees of freedom. Anytime you name a T distribution, it is very important that you name with it how many degrees of freedom it has. So this is a T with 2 degrees of freedom. So one thing you'll notice here is that the T distribution is actually heavier in the tails. Now, what this will do, going to the T distribution right here, this one right here with the thicker line, is actually going to have more area underneath the tails. So what this means is our confidence intervals are actually going to be wider. Because think about this. If I wanted to cover 99% of this hashed one, well, there's less area out here on the sides. I could make a tighter confidence interval and still get most of the area. So when you push this down, when you take a normal and push it down, you're actually pushing the area out. Now, what this does is very important. It makes our confidence intervals wider. With a wider confidence interval, we're more likely to have the true parameter in our interval. So what formula will we use right here? This formula is eerily similar to everything we've been doing. Anytime you see a confidence interval, it is going to have the following formula. First, we will have what we're trying to estimate. We are trying to estimate the true mean. And our best guess of the true mean is the sample mean. So in this first part, you can look at it as what you are using to estimate. You are using the sample mean to estimate the true mean. The second part of our confidence interval is going to be our test statistic. The test statistic gives us our confidence level. So this t, and this is subscript right here, n-1 degrees of freedom, tells you that we are going to have a t% confidence interval. The level of our confidence interval will be determined by the test statistic. Now the final portion of our confidence interval is the standard error. So we have a standard error for this confidence interval right here as described by s over the square root of n. Very important we realize that our confidence interval has three parts. 1, our best estimate. 2, our confidence level. And 3, we have our standard error. If we want to do the estimates right here for this problem, let's take a look at it. We are going to make a 90% confidence interval. We have data on 23 cars sampled on April 11th, 2014. So let's see if our assumptions hold so we can use these techniques. First, we have randomization and 10%. We need to make sure that the cars are randomly sampled and that the cars are less than 10% of all cars. These are pretty safe to assume, but any problem on any test should say, we randomly selected these cars, and 23 cars we could assume is less than 10% of all cars. Next, we have the nearly normal condition. The nearly normal condition states basically that our sample size is large enough. We could do the nearly normal condition with a goodness of fit test on the histogram, but we don't need to do that if the sample size is large enough. Now the rules we have here are for small samples, it needs to look pretty normal. For moderate sample sizes of 15 to 40 or so, it needs to look a little less normal, and it's not that it needs to, but it can look a little less normal. When we have large samples, it can be really skewed for 40 or 50. If you'll notice, this is the central limit theorem in practice. This allows us to use the normal techniques here. So checking these conditions, we seem to be pretty good. We seem to meet everything needed. We have randomly selected, we have the 10% condition, and then we can actually look at the shape. And looking at this right down here at the bottom, that looks unimodal, it looks slightly symmetric, and it even passes a goodness of fit test. We see here the p-value is not low, so we do not have evidence of non-normality. So we're good. Yes, let's go ahead and get to the data. This is where it's all at. This is what we've been building to right here. So with this in mind, one of the big things we have going on right here is we have our sample size, our sample mean, and our sample standard deviation. Now that's not on the slide, but I want to make it clear. Sample size, sample mean, sample standard deviation. And there's the notation, n, y bar, and s. We can calculate the standard error of y bar. That is simply the sample standard deviation over the square root of the sample size. And if you remember back to the formula, that's all we're trying to do right here. All we're trying to do is run this formula. So we needed this right here in the formula. Where people get tripped up in these problems is they have a hard time finding t. Now the degrees of freedom for a one sample t-test, a degree of freedom for a one sample t-test will be n-1. Let's take a moment. n-1. What is it? n-1 will be 23 minus 1. So the degrees of freedom is 22. Now let's look at something. Let's go over to an applet we haven't seen before, the t-applet. This can be found under the applets on MyPearson. Here we are looking at the applet on MyPearson. And what you'll notice is this is a t-distribution applet, and the first thing it asks you for are the degrees of freedom. So we can enter in 2 here just to see it, and go to 3 and 4. And you say to me, Brian, it looks like that's getting wider. And it does. It does look like it's getting wider. But if you look at the scale on the bottom is really wide to start. And we wouldn't see this much area outside of 3. So if I put this to 20, you'll notice 3 is, it looks more like a normal right now. It's actually just zoomed out when we have very few degrees of freedom. So you would not see the tails this heavy. Just take a look at where 3 is right now. This is actually pressed down if you put it into perspective. So you see 3 right here has this much area underneath it. You can stick the whole thing underneath it right there. And then if we go to 100 degrees of freedom, if you go over to 3, there's no area. And this looks just like a normal. The t just wants to be normal. The more degrees of freedom it has, the more degrees of freedom it has to be normal. At this point, with 100 degrees of freedom, you could probably just use the empirical rule. And I mean that. A lot of people at this point would just use the empirical rule. But we're not to that point when we have 22 degrees of freedom. With 22 degrees of freedom right here, and I think we have this entered in. Let's just test. There's 2, and there's 22. With 22 degrees of freedom, we're not going to have the ability to use the normal techniques. We need to, in fact, let's put in, we want to make a 90% confidence interval. And a 90% confidence interval is going to have 0.05 on each side. Think about it. If 0.05 is over here and 0.05 is over here, and let's view that visually. Let's put 0.05 over here. This would be a 90% confidence interval because 90 would be in the middle. 90 would be in the middle between these 2 points where 5% is over here and 5% is over here. This makes a 90% confidence interval, and the t-statistic is 1.71715. And you see that right here. And we get the positive and negative from it because you say, Brian, wait, wasn't there a positive and negative? That is incorporated into the problem. In the problem itself, you have the positive and negative of that critical value. So we can pick this, and we made it a 90% confidence interval, and we found it. The applets are on my Pearson once again, so you can go ahead and use them. So let's see right here. We plug in everything, and look what we get. We solve out. We take 1.717 and we get the margin of error. This part right here, the plus or minus, is called the margin of error. The center of it is called the best estimate. So we have our best estimate and we have our margin of error, and that creates the interval. And we've seen this with proportions. This is 31 plus or minus 1.5, and look at that. It makes a nice and pretty interval. The interpretation here is very important. We would say we are 90% confident that the true mean speed of all vehicles on Trip Hammer Road that day was between 29.5 miles per hour to 32.5 miles per hour. So there might be some sort of bias in here, and this is more of a response bias if you think about it, because if the drivers see it and they change what they're doing, they're changing the data we're collecting, which is the response. So a little bit of a response bias couldn't be in here, but not for certain. It's a possibility. We can use Excel to do this right here. Excel is great for doing confidence intervals, and you'll have access to it outside of UT. I love using Jump, or I just like doing them by hand. But Excel has a lot of ways to make confidence intervals. So go ahead and review this or use this if you like. But Excel can do a lot of the work that we're doing in this class for you. Just looking through some example right here of how to do it. Just enter in your data into Excel and then run the confidence interval. When we make confidence intervals with Jump, we get a little bit more output. And looking at this right here, we have a 95% confidence interval. This is the same data right here, where the sample size was 23. And notice something. The confidence interval before was 32.5 to 29.2. This confidence interval we get right here is actually wider. You're going from 90 to 95. That makes a wider confidence interval, and always will when using the same data. A 95% confidence interval is going to cover more area. So we have the same sample size, we're using the same data, and now we have a 95% confidence interval. And Jump calculates it for you right away. I am 95% confident that the true average speed on the road of cars on this road that day is contained in the interval 29.2 miles per hour to 32.8 miles per hour. The t-distribution calculator and everything is excellent. I suggest using the applets we have on the page. They're nice and easy to enter stuff into. Get accustomed with them because you could be confronted with some pictures on the test showing you what would your value of t be, or how would you obtain this value. Now, as I mentioned before, and this shows specifically, if I'm making a 90% confidence interval, I need to put 5% on both sides. Think about it. 90% in the middle means 5 is left on both sides. It has to be a 90% confidence interval. And this is shown by 5% being on either side for a total of 10% outside the interval. It's like when we do 68% in the middle with 32% on the outside, just like our 68, 95, 99.7 rule. So here you go. Here's another applet picture showing what we've done before. This is 5% on one side of it right here, and we'd have to duplicate that over here to make 90% in the middle. 90% in the middle puts 5% on one side and 5% on the other. And since this applet can't, like the David M. Lane applet, just do that for you, you have to do one tail at a time. And we're not doing a one-tailed test, we're just making a confidence interval by doing one tail. So let's go ahead and do an example right here. We have 52 adults, and we have their temperatures. So let's make a confidence interval for it. Were these 52 adults randomly selected? Well, the problem says it. Awesome. Are they less than 10% of all U.S. adults or all adults? Sure, sounds good to me. There's more than 520 adults in the U.S. Next, we can look at the histogram first. Well, that looks kind of normal. I mean, I could change the bins a little bit, little right skew. Sample size was 52 though, which is a big sample size, so I can do a lot of leeway. This is how the nearly normal condition is done. You look at this, you say, would the distribution of means be nearly normal according to the central limit theorem? And I'd say yes. Even more so, the distribution itself is normal. Well, we don't have reason to believe it's not. So if the distribution itself is normal, the distribution of means will be even more normal, so we're good on the nearly normal condition. We want to make a 98% confidence interval. So let's switch back to our applet that I love to use right here. Let's go ahead and make a 98% confidence interval for this, where we need to find the degrees of freedom first, which is going to be 51. This is obtained by n minus 1, which is 52 minus 1. And now we need to give it the percent outside the interval, which is very easy with a 98% confidence interval because it's 1% outside on both sides. If I have 1% here and 1% here, that's 98% in the middle. Now we'll round this to 2.4 for our sake, but on the test I might carry it a little bit further, but for all intents and purposes, this 98% confidence interval for a t with 51 degrees of freedom is going to be 2.4. So let's go back here. And now it's just plug and chug. Because remember, this stands for a t with n minus 1 degrees of freedom. This is 2.4. The standard error of y bar is what we have to find. So let's go ahead and click in here and find the standard error of y bar. We need to take let's take 52 first and do the square root. Because if you notice, we need to do s divided by the square root of n. So I take the square root of n, I copy pasted it. 0.68237 divided by the square root of 52, which I already had saved. And we get that for the new standard error of y bar. I'm going to copy this right now, and I'm just going to times it actually. I lied. And I'm going to multiply it by the t-statistic. The t-statistic times the standard error is going to give us the margin of error. So my margin of error is 2.2271. I'm going to copy this because I'm going to need to use it twice here. Remember, this is the margin of error. So I take the estimate, the point estimate or best estimate, and I subtract the margin of error. For 98.06, that is our lower portion of our confidence interval, 98.06. So I'd write that down now, 98.06. And then I would take my best estimate again. And what do you think I'm going to do? I'm going to add to it the margin of error. 98.062, 98.51. I'm 98% confident that the true average temperature of adults is contained in the interval 98.06 to 98.51. This is our interval that we've created right here. It's a 98% confidence interval. This is excellent, and this is the point of this chapter and what we've been trying to do here. So what about if we want to do a test? Everything is going to look very similar here. Very, very similar. So we are going to come up with hypotheses again. First thing we need to do here is we need to have a null hypothesis. We can only use data to make these decisions. If we think about a confidence interval to begin with, it's similar to running a test. A confidence interval is telling you I am 95% confident that the true value is one of these values. So a 95% confidence interval is like running a test. It's like a two-sided hypothesis test where your alpha level is 1 minus C, and C stands for the confidence level. So in a lot of instances, if you make a 95% confidence interval, anything outside of that, you can reject at a 0.05 level of alpha. So we've already been doing tests right here. Going back to our example with the temperatures for adults, if I told you, do you think the average temperature for adults is 99 degrees? If you remember, our interval only went up to about 98.51. 99 degrees is outside of the interval, and we could reject it. You say, no, 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 that's outside the interval. That does not seem like a value that could be possible. But let's look more specifically on how to do tests right here. Our null hypothesis is a value you would believe without any evidence. And if the parts per million right now for this insecticide is believed to be 0.08, we would have problems if it was above 0.08. But this is kind of the current belief. Now you might say, well, why would you believe this? Maybe it's in the past. Past research has suggested this. Maybe they're saying, okay, there won't be an audit on the company if the levels are not shown to be above 0.08. So they say, okay, well, let's say it's 0.08. Do we have evidence to believe it is above 0.08? So a lot of times it's something they want to test out. It's the current belief, and it's what we're starting with. So this is the null that is equal to 0.08, and they want to see if there's evidence for the alternative that it's greater than 0.08. So very important to be able to read this. When we read this right here, it says, the null hypothesis states that the true mean level of insecticide is equal to 0.08 parts per million. The alternative hypothesis states that the true mean level of insecticide is greater than 0.08 parts per million. Data that would lead us to reject the null would be data that is much higher than 0.08. We'd have to follow it, and we don't know right now, but maybe 0.09, 0.10, 0.11, or 2. 2 sounds like a very big number for this. Something larger than 0.08 would lead us to reject the null and show evidence for the alternative. So here's our new formula. If you notice, this time we solve for a t. The t is going to tell us how far away we landed. And just look at the formula. We're taking a distance that the sample mean is away from the null mean. This is the null mean. If you notice, this is the way we state our null hypothesis, is that the true mean is equal to some null value. So whatever you pick right here is what you're testing. This is the tested value. Your null value is what you currently believe, and then you're seeing how far away your sample mean is away from it. Remember, if this is like 0.11 and this is 0.08, just solve kind of an easy problem right here. If this is 0.11 and this is 0.08 and this is 0.01 down here, this whole thing would solve for 3. And t's are like z's, they're not the same, but a t of 3 might sound big because a z of 3 sounds big. They're not the same, they're similar. But if we think of a z of 3 being big, a t of 3 would also be big. So remember, all you're doing here is basically finding a t-score, which is just observed minus expected standardized. This is what we've been doing when we find a z-score. We just take the observed minus the expected, and then we standardize it. We're going to do the same thing here, but our standardizing factor will be the sample standard deviation over the square root of n, what we've been using before. And remember, this is for means. This is very good to write down at this point that this is what we'll use for means. This is the new standard error of the mean, and will be used for means in confidence intervals and means for tests. So let's go ahead and check some conditions right here. We need to randomly collect this data, and this would have to be stated specifically in the problem. It would have to say this data was randomly collected. So unless it does say that, we're good. If it doesn't, that's not so good. Is it less than 10%? 150 salmon is less than 10% of the population. Sounds good to me. I bet there's more. I hope there's more than 1,500 salmon. Hopefully we haven't ate them all into extinction yet. The nearly normal condition. Now remember, this sample size right here, how many did we get? What was our sample size? Now here we go. Aha! N equals 150. With n equaling 150, now we know for certain. Nearly normal condition is met because the distribution of means for sample size larger than 50, we're good. We have the standard deviation now of the sample. We need to turn that into a standard error by dividing it by the square root of the sample size. The mean right here is just going to be the mean. Look at the formula. You take your observed mean minus your null mean, observed mean minus null mean, over standard error. Observed mean minus null mean over standard error. To see the formula again, observed mean, sample mean, which is just your observed mean, minus your null mean, that's what the null little symbol there for, like the null guy over there, over your standardizing factor, which is your standard error. And we just see the same thing right here. This gives us the t-score. And as we notice here, it is very close to 3. So with this in mind, we keep talking about this 3 thing because it's always meant to us something that is an outlier. And I want you to think about something here. Remember before how I said the t basically becomes normal? Well, with this in mind, since the t is almost normal, this is basically a z-score of 2.8. Is that kind of an outlier? It basically is. Looking at this right here, we can see on this distribution that the probability of our results or results more extreme. Looking right here at this distribution, we can see that the probability of our results or results more extreme is very small. We only had a 2 or basically 3 out of 1,000 chance of getting our results or results more extreme given that the null is true. So I would say that this center value here, because this is where we should have fallen if the null was true. Think about it. If we had obtained 0.08 and then we tested it against 0.08, this solves out to 0. Divided by this is still 0. That's a t equal to 0. So according to the null, we should fall right here. This is exactly where we should fall. And the only way this red area gets smaller, as we said, is if we fall above. Remember we said if values of 0.09, 0.10, actually 0.09 somewhere up here, 0.09, 0.10. It's only going to happen that we fall t statistics away when we obtain values above, because that's going to lead us to reject the null. We wouldn't show evidence that the true mean is greater if we fell below. So with this in mind, this was not likely to occur by chance. What we saw here leads us to reject the null. And what more do we notice? This is a t distribution with 149 degrees of freedom. Where did that come from? It came from n-1 right here. n-1 is 149. That is the t distribution we are using right here. And if you were to compare this to a normal, well, let's go ahead and compare it to a normal. Our t statistic was 2.804, where our z statistic is 2.759. This is so very similar. And you can't, let me just say this, you can't just use z's. We're using t's for a reason, but they become more like the z with more degrees of freedom. So the t is specifically designed for smaller sample sizes. It has the most usage there. All computer programs will default to using a t even for very large sample sizes because it is just more accurate. And at times, it's really going to matter. When the sample size is small, you'll see big differences between the t and the z. But when the sample size is 149, well, it's very similar. If we go to the same amount of area on this normal curve, which we had on our t statistic, then we would find a z statistic of 2.759. If we enter in the reverse way of putting in above 2.804, and I'll move the screen down, we instead of getting 0.0029, we get 0.0025, which is very, very similar. But the accurate and correct way of doing it is with the t. The biggest differences will be seen when the sample size is smaller. So don't use the normal for this chapter. Do not use it. We only use the normal when we know sigma. I usually say sigma z, s, and t. So sigma, you need to use z. S, you will use and use t. Looking at jump, we have the results here exactly. Now, if you'll notice, jump shows us all 3 hypothesis tests. We have the two-tailed, we have the greater than, and if you just point right here, probability greater than t, and that points to the right, so that's the shading to the right, the very small area. And probability less than, which is not shaded. That would be at this red line shading to the left. If you notice, the two-tailed is also shaded. It's very hard to see. It's that little tiny area right there, and this little tiny area over there. That's 0.57, which is basically double 0.29, because apparently there are some decimals we can't see. The left and the right tail always add up to 1, as we've talked about before. These two add up to 1 because you're just shading all the way to the right, shading all the way to the left, and you'll shade 100%. And the two-tailed is double the smallest. So there's decimals we can't see. Usually these look more like it would be 0.29 and 0.58, but because of decimals we can't see, there's a difference that comes into grounds. Now, with this in mind, we get a lot of the same estimates up here. We do not get the standard error, but we do get the test statistics. This was 2.8044 standard errors above the mean. Let's look at some cell phone batteries. Now we're going to test 12 cell phone batteries here. If you notice, this is a much smaller sample size, so very important to notice that the T and the Z are going to be very different. This is one of the big instances when we would use the T right here. The null hypothesis right here, let's go back and read it. The company claims its standard batteries last longer on average than other batteries on the market. So we'd look at what the standard batteries last, which is 32 hours. And we would say that our batteries last longer than this. So to state them properly, the null hypothesis states that the true average battery life for our batteries is equal to 32 hours. The alternative, which we want to show evidence for, is the true average battery life for our batteries is greater than 32 hours. So here's our data. With our data right here, you can see we have a lot of 31, 32s, 38s. So seems plausible. And look at that. We have the mean and standard deviation. Ah, love it. Here's our mean. Here's our standard deviation. And here's our mean. Here's our standard deviation. And there's our sample size. Let's go through and look at the conditions. Condition 1, randomly selected. I believe the problem stated that these are randomly selected, so we're good. Condition 2, are these batteries less than 10% of all batteries? Yeah, I think there's more than 120 batteries out there for phones. Condition 3, is the distribution nearly normal? Oh, it's a small sample size. It's 12, and I don't know, that's got a little bit of a skew. Oh, but wait! We have a goodness of fit test, and we don't fail it. We do fine. So we can say this is normal. Well, looks normal enough, and that means the distribution of means will be normal to use the kind of normal techniques we're doing with the t-distribution. So we're good. We can do this right here, right now. So let's go ahead and compute our new standard error. Let's do the new standard error. The new standard error is going to be, let's take the square root of 12, and this is what we need here, the square root of n, which is square root of 12. And then let's divide the standard deviation divided by the square root of 12 to get the standard error of the mean. This is the standard error of the mean. Next, we need to take our observed mean minus our null mean. The null mean was what we were testing against, which was 32. And that would be 33.416667 minus 32. So that's going to give me 1.416667. And divide this by, I just did the first part in my head. And there's our answer on how many standard errors away. All we did is we took this difference and put it in terms of standard errors. So the last part here is what confuses people, because we need to use a specific t-distribution. Very, very important. We will use a t-distribution with 11 degrees of freedom. So let's go to the applet. So a t-distribution with 11 degrees of freedom. Punch it in right here, 11 degrees of freedom. Looks, see, it's a little heavy in the tails. Looks normal-ish, but no, we're not going to get very similar numbers to the normal. And then we need to put in our t, which is right here. And this is a very long number. It's my 2-point whatever number. And there we go. We want to find a right-tailed test because we want to show evidence that our batteries last longer. Because remember, right here is our value of 32 on this. It says 0, but if we were to land at 32, well, that would have been 0 standard errors away from the mean. So if we had landed at 32, we'd be right at the mean. We landed 2.42 standard errors above the mean. Remember, this is how we are doing it with the formula. The probability of our results or results more extreme, given that the null is true, is 1.675% or 1.675% chance. And that means it is very unlikely. It's less than a 5% chance, which means we can reject at the 5% alpha level. I reject the null that the true mean battery life is equal to 32 hours, and I show evidence that the true mean battery life is greater than 32 hours. So with this in mind right here, we can see the jump graphic with something eerily similar to what we've created. If you want, take a moment here and try to remember how we could actually find all the p-values. We could find all the p-values by plotting them in right here. We had our p-value of point, I believe it was 0.0167. Let's double check that real quick. There it is. 0.0167 for the greater than, and then the less than would have to be this way. It would go from here down. And then the two-tailed is just double 0.0167, so it would be double it right here. This is a great little thing for me to put on the test. I'd love to put this on the test, actually. It seems like a really good fill in the blank. Here's some of the numbers. but you would have to. These ones down here are easy enough to figure out. Remember, the less than and greater than add up to 1. The does not equal, which is the two-tailed, which is the darker color shading, and the lighter color shading, is always double the smaller one, which in this instance is the right tail. So this one right here, the two-tailed, the difference from the absolute value, or the probability greater than the absolute value, I should say, is double the smallest tail. Good luck, and if you have questions, email me.